So robotics 2 is a project-oriented course, which means there won't be that many, lectures, but we are going to focus on maybe 3 major projects, are pretty intense. So in the first 2 to 3 weeks, we are going to cover, like what I mentioned in the microcontroller class, power supplies, right? AC to DC, how to do that, transformers, right? And DC regulators, rectifiers, all these things. And DC to DC, buck converter, boost converter, all these things. And after that, I think we are going to move into the week 3, and we're going to cover all these different types of sensors, actuators that have been used, and or the other ones I haven't used before, but I have seen other people have been using that, all these sensors. So whenever you have a project, what are these sensors, actuators available on the market? I think that's critical, because any single robot has like tens or sometimes hundreds of sensors, right? Okay, after that, we will start our first project, which is a robot arm, which is not an industrial level robot arm, but a very simple one. But you will learn how to communicate, make the communication smoothly between two microcontrollers, which is basically just Arduino Uno. You have a robot arm with a decoder. We're going to learn what are decoders, and a replica. So you move around your robot arm, and the replica is going to move, just trying to replicate whatever has been done with the original robot arm. And the second project will be a 2-wheel balancing car. And there are 2 parts. The first part is mainly the theory, how to implement the PID control to, the stepper motors. So we're going to, trying to work with the stepper motors with different types of drivers. And finally, getting to the math behind the scene. So that's part 1. And part 2 will, you will be able to make it work. Let me drag it down to the video, but actually I brought it over so you can take a look. It's not 100% done yet. I was not able to have too many other things, but I'm thinking this can be a product in the future. So definitely this is not ideal, right? Everything was built on the blackboard, which is highly not recommended. So after you are done with the circuit, the hardware is not changing anymore, so you should convert everything to a PCB as soon as you can, because the wires can be broken and you can burn your power supply by some, incorrect connections. And I'm using a LiPo battery, which has how many cells? 3 cells. So a LiPo battery has 3 cells, and every single cell has 3.7 volts. So I'm actually getting 12 something volts, around 12 volts. And as I mentioned, the Arduino Uno the DC regulator can handle from where to where. Like in the morning, I just 6 to 12, something around that. So it's a little bit over 12 is fine. So I don't need anything else in the middle. So I can directly use this 3-cell LiPo battery to power up my Uno. And the Uno is going to regulate the 12 volts into 5 volts, right? So 5 volts for Uno. And the 5 volts, the regulated 5 volts output, will be the logic input for the motor driver to give a logic input for the driver. And that's it. That's how you design the power strategy for everything, just for now. And so this guy is able to stand on the table, and that's the only thing this guy can do. But in the future, we are going to integrate a remote, which I already purchased all these. What I think I forgot the frequency, but anyway, so the receiver is going to be plugged into this board, and you get a gyro stick, have another transmitter, so you can control this guy using a joystick. That's one option. Another option is you can see all these open source GUI on Android. So you can actually download it. I think the name of that software is called Easy GUI. So you can, directly use the joystick, the virtual joystick on that panel to control this guy. You just need a Bluetooth module. Plug into here to receive the signal from your smartphone. Pretty much the two ways you can control it, right? So you can move it going forward, backward. So I think the battery is a little bit weak. So I have to be really careful, when I'm trying to hold it upright, so I can make sure it's not actually going forward or backward. And it's not able to do too many other things. If I can do this, right? It's not a huge problem. But because the battery is not really strong as it used to be, and also the sensor was plugged into the breadboard. So you can imagine that it's not being soldered to a PCB, and whenever it shakes, it's pretty sensitive. So you are getting errors for a PID controller. That's why just after I push it, it changes its balance set point. So I have to reset it. It was trying to calibrate since I need to get the set point pretty accurately. So that's why I have to hold it upright for a few seconds, so it is able to calculate the set point should be stabilized at, right? So for the PID controller, and you can put something on the top. I used to put a water bottle on the top. It's still able to stand upright and not tipping over. So that's just whatever I have done. I'm going to provide everything to you guys: the hardware connection, the software, the code, everything. Okay, and what you need to do is, make this a product. I didn't create this. Okay? There's a person in the Netherlands. I think that guy made a version, but it's smaller. I simplified his code to a way shorter version and more easier to understand. So we are going to cover that in detail in the tutorials. And you will try to utilize the rest of the script on his website to integrate the remote controllers to the robot and convert into a PCB. So that's the most important project in this course. So the first one, the robot arm, is really not that difficult. Anybody can do 3D printing? Are you good at 3D printing? You too? Okay, I have a 3D printer. If you can draw all these parts, they are pretty simple ones and not, complicated shapes. So let's take a look. And this, the second one, will the two directly. Okay, so that's actually, yeah, this is a replica. Okay, so that's the arm itself, only 2 joints. So I found out this stepper motor doesn't have that kind of torque to handle 3, and I have to make it way shorter. And I just don't want to, spend too much time on 3D printing. So I directly just use all these wood sticks, and these ones are all these plastic bars, which can be inserted into the decoders. So actually, what I was doing is I move this first, and so all the movements will be replicated to the real robot arm later on. So you just need to push one button. So you have to design software to detect that push activity and then transmit all these series of movement being stored in the array in the first microcontroller to the other one, which is directly driving the robotic arm. So this is not really difficult, but I do need, if James can do that, please probably 3D print the arms, and so we can print probably 7 copies for everybody, if that works. Okay. Otherwise, we have to go to the shop to drill it, cut it. Do you prefer to like that? I'm really not a mechanical person. I don't want to do that. You? Really? Okay, if you want to cut it, then how many can you cut? All right, we'll talk about it when it's closed. And the third one, I haven't posted online, so that will be a vibration detection, like we just talked about that. So I have a, it's a complicated project, but now it's only in phase 1, according to the sponsor. But in phase 2, I really want something can be detected in real time. So the project, the background of the project is there's a couple investors are interested in detect the lameness of horses, but actually it's hard to tell when they are just by looking at the horses. They have to be super experienced at doing that, so they can tell the lameness of the horses. The industrial standard method to detect that lameness of horses is using a very expensive tool called some laser method. So you're using optical lasers to detect the differences of the movements, the displacement of the limbs of the horse. And that one cost like over $100,000 for each setup. So they are trying to, embed the sensors into the horse shoes. So they want to cut a hole on the shoes and embed a battery in there and wire, and then extend the wire to the top and to power up the module, your CPU and everything. So that's for one shoe, right? So you have 2 shoes, parallel shoes, then you need a 2. And if you need 4 sensors, you need 4 nodes in the same network. And so in this class, I don't want to do 4, right? So since we are still in phase 1, and in phase 2 probably, but in phase 1 I just need 2. And the signal has been successfully transmitted to the data center, and you are going to build this since you guys are in group 2, probably all of you guys, right? So I have everything already uploaded to my website in my controllers. So that's for the first part of the project. I already have 1 node which is able to detect all the acceleration data, the gyroscope, which is the rotation, angular speed, right? So angular speed and also acceleration, which are being used as diagnostic parameters for detecting lameness. So it's done, which means I can have the data center receiving all these acceleration data from the node. So the second step right now is, can I detect the lameness in real time when when the horse is wearing all these sensors under the hoof? So can they detect lameness whenever that happens? So we don't have to install this to horse or to horses. What we need to do, probably we just want to mimic that. You can, put it under your shoes, and if you just walk normally, and you train that data, use your machine learning model, so that will be counted as normal gait or normal walk. And if you try to mimic that, like, paralyzed or something, and see if your machine learning code can detect that or not. Very simple. It doesn't have to be industrial standard, like to be ready to sell to big companies. So we want to, just trying to practice with, how to build a machine learning model in an embedded system instead of using laptops. Probably you can take a machine learning course online really easily, like the machine learning crash course from Google and all the other things, and all the examples in the recommended textbook. So we don't have an official textbook for this course, but we have a recommended one for the very last project. Can be a good reference for you guys to learn it as beginners. But however, how to do it on the embedded system, right, can be a little bit different. So we're going to use Raspberry Pi, which you used in your Python class. It's a small-sized computer which can be mounted to, the horse easily, I think. We can use other computer platforms, but I think Raspberry Pi probably is the easiest one to get something done. It doesn't have to be, like what I said, ready to sell. What I need to do is, I don't even need to get this done in 3 months in this fall because the investors are not interested in, get everything done in 3 months. What I need to do is only get this signal transmitted to the data center, to nodes. My sensor node inside the shoes can, stay there, can survive for at least 1 hour after, the horses tracks. Just 1 hour. Then I'm done for phase 1. So phase 2, maybe, there will be, I don't know how much money, but, like what they said, can be $1 million, can be less. This is currently the most important, I'm sorry, but last year, the EPA was the most important project in my life. No, EPA was not. So this project is the most important since it's really, we can have some industry partners be interested in, working with professors and students in Forest College will be really good story to tell. And also, the money comes in, it's supporting not Forest College, but also students as well. And also, we can buy equipment, we can do a lot of things. And I think you guys can get some real world experience, not just working with something, right, just in the lab. You have to consider all these constraints when you are trying to apply this into a real life, like the stripes, the data, power supply. The size of the battery cannot be too big because the shoes doesn't have much space to embed that battery. So inside to fit that battery in. So that's the 3 projects we are going to do in this class, plus all the projects in microcontrollers. What you think in 3 months? You? It's exciting? We'll see, okay? If you are not able to, I'm gonna see your progress. If, we are not, for example, we are not getting the 2-wheel car done, I'm not trying to, start the machine learning project. Let's see. Okay. Any questions? No? All right. By the way, are you still able to work on the EPA project, James? Okay, yeah. So you're planning on working on that as well, isn't it? Cool. So it's one more project for you. How many projects do you have, Spencer? Okay. Let's start working with the AC to DC converters. See what we need to know. AC to DC, what kind of device you want to use? AC to DC. Transformers. right? Oh, no. Transformers plus rectifiers. Okay. So transformer. Something like this, right? And there will be an input voltage, which is definitely AC. And here's the transformer's symbol. AC, right? You need a rectifier to rectify out all the AC ripples. So the first thing I want to let you know is the half wave rectifier. So that's the output, that's the load. And this is called half wave. Rectifier. So the reason is you're only getting 50% of all the bumps, all the waves as the output. Let's draw it. Take a look. That's a diode, right? So only allow the voltage going from here to here, but not backward. Okay. And here's the input. And the diode has a VB, which is the built-in potential, for example, 0.7 volts. So which means it's going to force the voltage drop from here to here. And the voltage drop is 0.7 volts. You couldn't change it. It's going to force it to drop 0.7 volts. Keep in mind. So I can draw the little bar here. I know it's higher than it should be, but just trying to make it more significant. So that's VB. And I call this VM, V maximum, VM, V peak. Okay. So what VO looks like? So whenever it's going, so the top, when the top sound wave, the top half is passing through this guy, it has to overcome this 0.7 volts in order to get anything conducted, right? It has to be higher than 0.7 volts. And when it's going downwards to the negative half of the sound wave, what's going to happen? So it's like higher, lower. At the bottom, it's higher, lower. It's blocked. So that's why what you're getting is you're not getting anything here because that's a built-in potential. You have to overcome it in order to get anything conducted to the other side. So you are getting something like this. And it's going to be flat here as well. And then nothing because it's blocked. And then again, it seems like that. So that's a VL. So now let me know, what's a VP here? Yeah. It's a little lower than VM because there's a 0.7 potential drop, which is forcing the voltage to drop 0.7 volts. Okay. But ideally, the rectified output should look like what? This, right? Okay, but actually it's not. So if we are looking at, let's say, probably this one, the ideal one, there are three parameters you need to calculate. So let me write it down first. That's the ideal case. Okay, that's a real case, that's the ideal case, that's the input voltage. So there are 3 parameters you need to know how to calculate. So the first one is VF, V average of this guy, of the ideal case. So that's a rectified. That's for the rectified output. Okay? V average equals to what? If we know this is 2 pi for one period, it's 2 pi. So here's 2 pi. So the average, we need to use integration to calculate the average. It's 1 over 2 pi. So it's the integration over this period of the voltage, and then divided by 2 pi. So that's how I calculate the V average. So that equals to 0 to 2 pi. And the sine wave, because you know the peak voltage is Vm, and because this is the ideal case, so this will be Vm as well, right? Ideal case, no voltage drop. So the sine wave is actually Vm times sine omega t, d omega t. Vm sine omega t, d omega t over 2 pi. That's the way you calculate the average voltage. And you can split this because the second half is 0. So from a pi, when you are integrating the pi to 2 pi period, you are getting zeros, right? So if you split this one, it's going to be 1 over 2 pi, and 0 to pi will be Vm times sine omega t dt plus pi to 2 pi Vm omega t. Omega is angular speed, angular velocity, right? So times t will be the angle. And the second half is 0 because this is 0. Integration result is 0. And only this part, because Vm is a constant, so take Vm out. And integrate from 0 to pi. And you have sine omega t d omega t left in there. And this equals to b Vm over 2 pi minus cosine. Since the derivative of cosine is minus sine, right? So we need a minus cosine. So it's going to be minus cosine. All right. The entire thing is x, right? Because this is x, x, x. Good to check. So these are x. So what is the result here? Vm over 2 pi. What is cosine pi? Pi is here, right? What is cosine pi? So here's a little bit higher than pi, smaller than pi. What's this angle? 179.99999. What's the cosine of this angle? Assuming this angle is tiny, this is negative something, r. This is r. What's cosine 179.999? That's the way you can remember cosine 180, right? Did you get that? So let's think about that. What is sine 90? 1. Why? Because if you draw an angle here, and this angle is 89.99999, and 1,000,000 So what's the sine of this angle? It's going to be this one divided by this one, right? Oh, no, sorry, this one. This one divided by this one, because it's going to be the arc opposite to this angle. So this divided by this, which is 1, because they are getting closer and closer, right? That's how you can remember this. So what is the sine 0? Sine 0. That's 0.0000 something, 1 degree. And this will become 0 eventually. So 0 minus 0 divided by, or 0 over 1 will be 0. So that's sine 0 is 0. So same thing. Cosine pi will be something close to pi, which is this guy, which is 179.999. And what's the cosine of this guy? You draw this line here, and it will be this line over the radius, right? What is that? -1. Is that -1? Because whenever this is closer and closer to and overlap with this line, it becomes pi, and it's giving you that -1 result. So it will be minus 1 minus what? So what is cosine 0? 1, right? Confusing? What's the result? Don't get frustrated. It's not. It's easier than you think, than you thought. But so here are some prereqs. Okay, do you still remember how to get this one from here? You. That's in calculus 2 or 1? 2, calc 2. So if you are frustrating, probably from here to here, you don't know why, right? It's pretty simple. Just go back to the book and look at the equations and whatever theorems you need to remember. Just record the memory, see how that works. No worries. I was super bad at calculus when I was in college because I just never go to the class. Because the professors didn't ask us to go to class, and I was not motivated. I was thinking, hey, in college, shouldn't I just play basketball and not dating, but dating and and any other things, right? So do also social activities. I didn't like it, but finally in the 4th year, we have to work super hard on this to get into graduate school. So that's where I picked everything up eventually. But you do need someone to tell you what to learn in college, which I didn't have that kind of professor to tell me. I was always thinking I should go to graduate school, so I was not super anxious about the life after my life after college. So I know I have time to make a decision for what to do in the future. But anyway, eventually I found out, that's a kind of precise, right? So I was in a major. The name of the major is bioelectronics, so biomedical engineering. But we are making all these amplifiers for ECG detectors, all these kind of sensors, and you learn that, and you find out, hey, I don't understand how these chips are working. And I go to my master's. I pick up the really good lab, and the professor is probably the most famous one to get the students into the industry because they they know how they all they are doing are embedded systems. So I was really happy about that. And I realized actually whatever you are doing, as long as it is related to embedded systems or software, you need to learn that. You couldn't just pick up a some major which only has really limited access to these technologies. You won't be ready for a job in the future. So, okay, from here to here, if you're not familiar with that, go back to your Calculus 2 textbook and see if you can make it. And from here to here, let's write it down. I see the frustration on her face. I put bad comments on my teaching evaluation, so I have to repeat it. Okay. Let's do it. Okay, from here to here, I'm going to skip it. Is that okay? Since, I didn't invent it. I just from my memory from the calculus tool. Is that okay? If I skip from here to here? Okay, so now here, you have Vm over 2 pi, which is a constant in the front. And you have this guy. Instead of letting this negative sign confusing us, I'm just extract it and put it here. Will that work? Okay. And then cosine omega t, which is the entire thing is the x. So keep in mind, t is not the x. Omega t is the angle. And okay, next. Then what? Cosine pi and cosine 0. What are they, right? Do you know what are they? You? From here. That's the easiest way you can remember this, right? So that will be, what is this? -1. This, what is this? Times what? So what's the final result? And what is this? It's been so long, I forgot what we were trying to calculate. That's average voltage. That's how you calculate the average voltage output. And sometimes, probably on the homework assignments or in any other textbooks, you will see they'll ask you what is the DC output voltage? The rectified DC output voltage. So this is actually the average voltage output or the rectified DC output voltage. Okay, so that's the first one I want to calculate. And the second one is the RMS. It's a pretty important concept you need to know. Okay? So when we are talking about the 110 volts power supply available in the outlet, right, in the wall, what is that voltage? The peak voltage or is it RMS voltage? So first, what is RMS? Root mean square. So the 110 is peak or RMS? RMS. Okay, good. So for this half wave rectifier, what's the RMS current as the output? So we are calculating the by the way, here, I need one more step. So that's VAV, right? That's average voltage. So what is IAV? Average current. Average current is VAV over R load, right? Do we have a load? Yes, you do. So what is VAV? VAV is VM over pi and over RL, and which is the same as VM over RL over pi, right? So VM over RL will be IM. So IAV is actually IM over pi. Do you agree with that? You do? Okay. No worries, it's recorded. Okay. So that's average voltages and currents. Now let's look at the RMS. IRMS equals to what? Root mean square. That's mean, that's root, and then you still need square. Because this guy doesn't have anything from pi to 2 pi, so we just ignore that. So we only integrate from, yeah, let's integrate from 0 to 2 pi because we're averaging over the 2 pi range. So 2 pi, we're going to, cancel the second half later. So Im sine omega t is the current signal, and square, so it's squared for both of them. So that's root mean square. So that's RMS. And that's the equation. We just need to derive, what's the final value. Yeah, 1 or 2 pi. Yeah. And yeah, let's move forward, see if we can get this done. Root 1 over 2 pi, 0 to pi. You have this because it has signal from the first half, and the second half is actually 0. Sine omega t d omega t plus 0. You can definitely extract Im because that's a peak current, which is a constant. Don't forget the root, square root. All right, calculus 2 again. Calc 2 again. How and why? Do you know that cosine 2 theta equals to cosine theta square minus sine theta square? Did you learn this? And 1 equals to cosine theta square plus sine theta square. You learn that? So from these two equations, I'm going to use 1. So left minus left, right minus right. So it's going to be 1 minus cosine 2 theta equals to 2 sine theta square. So you can build a connection between sine theta and cosine 2 theta. Because you have a sine theta square here, right? So sine theta square equals to 1/2 of 1 minus cosine 2 theta, right? And then sine theta square, so I can use this one to replace this guy, which equals to going to be half of 1 minus cosine 2 omega t d omega t. Is that correct? And 1/2 can be extracted from here, from the integration. So I'm getting Im square 4 pi okay, and then I'm getting so that will be pi minus 0, which is pi, and let's do it step by step. So I'm not skipping too many steps to reduce the frustration. Is that correct? Okay. Pi minus what? Do the integration here, which is pretty simple because sine pi is 0, sine 0 is also 0. So the entire thing here is going to be 0. No worries. I'm not expecting you guys can. You just need to calculate this when you are considering all the power supply requirements for anything, not just robots, anything else. But I really expect you guys make the products work, not this, which is fine. Okay. I need the products. I want to sell it. This is just in the homework assignments. You know how to do it in the future. If you forget, come back to the notes, the lectures. You can still calculate it. All right. And what's going to happen next? So pi canceled. So you are having Im square 4, which looks pretty nice, right? Im over 2. So that's the RMS of the half wave rectifier. So now, what is VRMS? Let's do it again. Start from. I'm not. We only have 2 minutes left. So VRMS equals to IRMS times R load, which is, what is this? It's here. I'm going to combine these two. What is this? This is a VM. It's going to be VM over 2. Okay? Keep in mind. So these key parameters you need to know. VRMS, IRMS, VAV, IAV for half wave rectifiers. And we're going to calculate the efficiency and other things you need to know when you're designing a power supply, and also the full wave rectifiers. 2 types of full wave rectifiers. One is called the bridge full wave rectifier, another is called center tapped full wave rectifiers, and they have different efficiencies and different RMS. And okay, that's whatever you need to know. So you guys don't have any homework assignments for today's lecture. And after Wednesday's lecture, we should be able to finish everything about the AC to DC power supply, and you should be ready to start working with the homework assignment. Okay? Okay, see you on Wednesday.